specifically focusing on how kernel and user space are mapped on x86-64 architectures. As developers, understanding this isn't just academic curiosity, it's absolutely critical for writing efficient, secure, and stable software. It's the bedrock that allows your applications to run reliably, isolated from each other and the core system. This knowledge becomes invaluable when you're debugging tricky issues, optimizing performance, or even just trying to understand a crash report. By the end of this lesson, you will be able to, first, understand the fundamental split between kernel space and user space. We'll demystify why this separation exists and why it's so crucial for system stability and security. Second, you'll learn how virtual addresses are structured on x86-64, looking at the specific address ranges and what those numbers actually represent in the grand scheme of your system's memory. Third, we'll explore the significance of memory protection and how it relentlessly safeguards your applications from interfering with each other and, most importantly, from corrupting the operating system itself. Finally, you'll grasp the practical implications for system design, giving you a much more informed perspective on how your code truly interacts with the underlying hardware and the operating system. Let's get started. At the heart of modern operating systems lies a critical division: the separation of kernel space and user space. Think of it like a highly secured building. User space is where all your regular applications run: your web browser, your text editor, your games. Each application lives in its own isolated room, preventing it from directly accessing or corrupting another application's data. This isolation is paramount for stability and security. On the other hand, kernel space is like the building's control room. It's where the operating system's core services reside, managing hardware, scheduling processes, handling memory, and ensuring overall system integrity. This space is highly privileged and protected. The beauty of this design is protection. It prevents a misbehaving user application from crashing the entire system or accessing sensitive kernel data. So, how does user space talk to kernel space? It uses a strictly controlled gateway called system calls. These are specific, predefined functions that allow user applications to politely request services from the kernel, like reading a file or allocating memory. It's a secure, audited pathway, not a free-for-all. Now let's zoom in on the specific architecture we're discussing: x86-64. This is where the virtual memory layout becomes tangible. While x86-64 processors have 64-bit registers, they don't actually use all 64 bits for virtual addresses. Instead, they typically employ what's known as a canonical form, meaning only 48 bits of that 64-bit address are actively used for addressing memory. The higher bits are either all zeros or all ones, creating a symmetric layout. This canonical form creates two distinct regions. The user space range starts from the very bottom, 0x00000000000000, and grows upwards. This is where all your application's code, data, and stack live. On the contrary, the kernel space range starts from a very high address, specifically FFFFFFFF80000000000, and grows downwards. This upward and downward growth creates a vast, unused region in the middle, often referred to as no man's land or the hole. This huge gap is intentionally left unused by the current architecture, providing ample room for future expansion without conflicting with existing address assignments. Understanding these ranges is key to interpreting memory maps and debugging memory-related issues. Understanding this virtual memory layout isn't just about knowing addresses, it has profound practical ramifications for building robust software. First and foremost is memory isolation. Because each process gets its own distinct virtual address space, a bug or malicious attack in one application cannot directly affect another, nor can it corrupt the operating system's core. This is a cornerstone of system security and stability. Secondly, It enables highly efficient resource management. The operating system can allocate and deallocate virtual memory pages without worrying about physical memory fragmentation. It can even swap inactive pages to disk, giving the illusion of more physical memory than is actually present. This protection is often enforced by protection rings, a hardware-level mechanism. The kernel operates in ring 0, the most privileged level, while user applications operate in ring 3 with restricted access. Any attempt by a ring 3 process to access ring 0 memory directly results in a hardware fault, preventing unauthorized operations. However, this also means debugging challenges. When issues arise within the kernel, or when user space code interacts incorrectly with kernel services, debugging requires specialized tools and a deep understanding of these boundaries, as standard user mode debuggers won't suffice. We've covered a lot of ground today, so let's quickly review the core insights. We learned that virtual memory provides vital isolation and protection, acting as the fundamental security and stability layer for modern operating systems. It's the reason why one application crashing doesn't bring down your entire computer. Then we explored how the x86-64 architecture divides its virtual address space into distinct user and kernel regions, with user space growing upwards from 0 and kernel space growing downwards from very high addresses, leaving a large unused gap in the middle. Crucially, we discussed how system calls are the controlled interface between these spaces. They are the only legitimate way for user applications to request services from the privileged kernel, ensuring security and preventing direct memory access. This understanding empowers you to write more resilient code and diagnose complex system issues with greater confidence. To test your understanding, consider this. How does virtual memory protect one user application from another? Think about the mechanisms we discussed today. Thank you for joining me on this exploration of virtual memory layout. Keep exploring, keep building.